Hello, this is heat exchanger simulation practice on Aspen HYSYS, working on shell and tail heat exchanger, and we have two chemicals. One is kerosene and one is crude oil. The kerosene will act in the hot stream and the crude oil is for the cold stream. The restriction on this case is to decide not to have the pressure drop greater than 0.8 into in both streams under the fouling factor of 0.0003 and 0.0002 watt per square meter degree Celsius, a reciprocal of that. One of the limitations is that the space that we have cannot put any heat exchanger longer than 5 meters. Particularly when we are working on the Aspen HYSYS, we don't know how to, we have to understand how to input the chemical which is not a pure component. And also, we don't know the temperature outlet of the crude oil. The red one stands for hot stream of kerosene and the blue one stands for the cold stream of crude oil. And the only thing that I know is the density of the kerosene on this range of temperature is about 770 kilogram per cubic meter and also 820 for the crude oil. This is average density. So what should I do for on this simulation? I start with input the component, and because the component here is not a pure chemical, it's a mixture of some species of hydrocarbon in the kerosene as well as in the crude oil, so we have to work on the hypothetical technique. Well, since we knew that the boiling point for the initial boiling point of kerosene is start from 150 degrees Celsius to 250 degrees Celsius. If I let the interval is 10 degrees Celsius as a default, after the generate of hypothetical, I can get some component which has each particular density. So I will select the range between the one that gives the density close to 170, which is on 150 and 160 here. So I add that as a component for the kerosene. And I will approximate that the mixture of 150 and 160 species here will be about 50 bar. And now I can look for the species that can represent the crude oil that have the density of 820 kg per cubic meter. So I change the initial boiling point and final boiling point to be 250 and 400 degrees Celsius. And now I can find for any representative species for 820. So I select the one which is close to like 240 and 250 here. Okay. Now I'm done on this. So I go to the fluid package. In the fluid package, if you don't know what kind of method you're going to use, you can use this help by clicking this and then find out for the component type. Of course, kerosene and crude oil is in hydrocarbon species, and this is containing of hypo component. We do not working on the vacuum condition. So what they suggest is this 3. I prefer to use SRK. Then I select the SRK as our thermodynamic method to the calculation for the calculation. Now I can start my simulation then. This is what I put it here as a crude kerosene and the crude out and the kerosene out. Then I place the heat exchanger, change the icon, and then we have to consider which one should be in the tube. We found that crude oil is dirty comparing to kerosene, so I put that in the tube. So that must be C and C out. I can scroll down and also kerosene and kerosene out. Then I have to complete the information of the input of the crude oil. The crude oil starts with 40 degrees Celsius, 6.5 bar, and the flow rate is at the flow rate of the kerosene 70,000 kilogram per hour. And this is the crude oil. The crude oil should be these two representative species. So I put it 0.5 in both species. So I'm done. Oh, sorry. I make it active. Then the crude oil stream is looking good. Then I'm move to the kerosene one. Put it half on this. Then go to the condition, starting with 200, with 5 bar, with the mass flow rate of 20,000. Okay. Now, go back and look at the question. The limitation on this is the pressure drop on both streams must be lower than 0.8 bar. So I specify on this 0.8 and 0.8 in the tube side. Then I need one more specification because after I check for the degree of freedom, I need that. So what kind of specification I should use. So I can check with this. I found that after a simple draw of the counter current, the kerosene is on the top, the crude is on the bottom. And then we found that the outlet of the kerosene have the temperature higher than the inlet of the crude oil for 50. So I use the temp difference and put that for the kerosene outlet and the crude in for 50 degrees Celsius. The simulation is stopped now and give us some temperature outlet of 78.24. Then let me check for the performance. It seems okay to get 0.875. Under 1, 2 shell and tube heat exchanger. So check again on the temperature and heat flow plot. Okay, it seems to be there is no heat cross between these two lines. So it's for the overall heat balance, it looks fine then. Now, after you get complete overall heat balance here, you can start working on the layout. Okay, now I can start do the sizing by the legless heat exchanger method by clicking this. And then you can take a look on this tab, changing to what we want, like 2 pass and 5 meter long, with the AEL type. What else that I have to input? The process. So I need to put the fouling factor to both sides. Make sure that you get the right unit. And also the temperature outlet of the kerosene is supposed to be 90 degrees Celsius. Well, let's see the result. Okay, I can go then to the model. Let's check what the calculation result are. So from here, there's something happened to this buffer because it's too many, and with the larger buffer pitch, so I reduce that to be 26, and then I change that to be 60. So let's see, they have the 3 warning system, and I would like to have 2 pass, so I go there and then make the pass detail. That's what I like. So the process tends to be like this. However, let's check for the process outlet. I want 90 degree outlet, but it's turned out to be 110, and I want 78. The result based on the configuration I have is 32, so I need to rechange that. I need more area for the heat exchanger, for heat transfer. So let's see. Let's see the tube layout. The shell diameter might be too small, that's why I cannot put more tube into here. So I start changing this outer diameter first to be 15.25. And then the inlet. See, based on this, you can fill in many tills. So let's check how many tills that they lay on that. So it turned to be 170. So I go back to input the number of tills to be 170. And then you have to make sure that the process is still running. When I check with this, I get the temperature outlet pretty close to what I want. Okay, that would be very nice. Let's see what I have in the layout. So it seems to be one shell and 2 tills. How about the geometry on the tilt side? So it looks good, and that is for the top part of one tilt pass, and the other tilt pass is in the one below. So what you have to turn it in is the thermal calculation based heat transfer and pressure drop. Okay, so telling that the HO equal to 1145 and HI is equal to 1115 based on the outer diameter, and there is no phase change. That's the Planck number and Reynolds number. Let's see the pressure drop. The pressure drop in the shell side is less than 80. That is the control pressure drop, and 27 in the tilt side. What else you have to turn it in? The heat exchanger geometry. So this is telling about 170 tilts for 5 meter long, 2 tilt pass, and then the tilt diameter, outer diameter, and the tilt pitch with a 30 degree. And that diameter for the shell, you have the front head and the rear head. And the type is in AEL with the buffer number of 60 with the spacing of 76, while you have the spacing for inlet is 178 here. So if you do not sure, let's see. See, there's a space here 178, while the buffer to the buffer is about 76 millimeter. Okay, I think that's all. You have to turn in this graph as well, so you can know that the temperature of the cold stream starting from 40 degrees Celsius, and then by exchange with the red line, which is a kerosene, this can be increased to about 78 degrees Celsius, and then the shell side decrease from 200 down to 90 degrees Celsius, as you can see from here. The calculation is missing from, it is about 0.5% would be acceptable. Alright, that's all for the EDR heat exchanger. It's very nice to understand and how to play around with the number here. If you don't know the number here exactly, just try one by one and make sure that the process, the simulation have been is still working. Okay, thank you, and you have a good day. Bye bye.